Section 6.5, Systems of Linear Equations, Matrix Inverses. Part 1, Definition of an Inverse Matrix. Two n by n matrices, A and B, are called inverses if A times B equals B times A equals the identity matrix, where I is the n by n identity matrix. So two matrices that are square are inverses if, when we multiply them in either order, we get the identity matrix of the same size. If B is the inverse of A, we denote B as A inverse, this symbol right here. If A has an inverse, we refer to A as invertible. So an invertible matrix means that there exists an inverse. And if B is the inverse of A, then A is also the inverse of B. Let's show that these two matrices are inverses. So if they are inverses, when I multiply them, I will get the identity matrix. So let's try that. If I multiply A times B, so here's A, here's B, and I'm going to multiply. First row, first column, I have -1 plus 2, which is 1. First row, second column, we'll get -1 plus 1, which is 0. Second row, first column, I'll get 2 plus -2, which is 0. And second row, second column, 2 plus -1, which is 1. So I did get the identity matrix. And if I multiplied in the other order, I would see I would also get the identity matrix. So if I did B times A, I'm still going to get the identity matrix. That's what makes the two inverses. To verify that two matrices are inverses, multiply them, and if you get the identity matrix, you know they are inverses. Another property that can be helpful is the associative property for scalar multiplication. So for matrices A and B and scalar K, such that A times B is defined, then K times AB, so if we multiply A times B and then multiply by K, that's the same thing as multiplying that scalar K times A, and then whatever that matrix is, times B. Or we could do K times B, and then as long as everything's in the same order, do A times whatever we got for the K times B. As long as the A stays on the left, the B stays on the right, we can put the K wherever we want. And that can be really helpful for something like this, where I have two matrices, and I'm saying show that they are inverses, but the second matrix has that scalar, the 1/12 in front. Now, I could multiply every entry by 1/12 right now, but then I'd have fractions. And then when I multiply the two matrices, I'm just more likely to make a mistake if I have a lot of fractions in there. It's just a little bit harder. So instead, I'm going to use this associative property. So I'm going to do 1/12 times this matrix A times the matrix B without that scalar in front, so just the rest of it. And this equals 1/12 times what I get when I multiply those two matrices. And then I will take that 1/12 and multiply it by everything in that product matrix. So if you want to pause and figure out that product, make sure you know how to do it, you can do that. But when you get this product, when we multiply, we get this matrix right here. So the first row, 12, 0, 0. Second row, 0, 12, 12. Third row, 0, 0, 12. And now if I take that 1/12, the scalar in front, multiply it by every entry inside, I do get the identity matrix. So these two matrices, A and B, are inverses.